My main motivation is to provide few videos on microcontrollers later. And since they can't read any value except digital data, it is important I give a brief insight here on analog versus digital signals and on how analog signals are converted to digital counterparts. I simply explain sampling, quantization, and encoding steps. Here I will not explain sampling theory and postpone it to another video for the sake of simplicity, simplifying the discussion to understand the concept of analog to digital converter. Most signals in the real life are continuous, such as temperature, heat, pressure, waves, and sound propagating through air and body movement, and etc. For computers to process these continuous signals, however, they have to be converted to digital representations via an analog-to-digital converter, or ADC. But the first step is to understand what is a signal, and then different types of signals. For example, in this figure, analog wave is shown as a smooth and continuous by blue curve, while digital one contains small discrete steps as an approximation of the analog signal. Let's dive into the problem. An analog signal is mathematically a continuous function of time or space. But in electronic framework, it represents information in varying waves of voltage or current in time. It means that the information in the form of amplitude, frequency, and phase are encapsulated in the wave form. Digital signal, on the other hand, can only take two values, either 1 or 0. This signal carries information in binary forms, as shown here, or the waves on the right hand side, which looks like a stepping and discrete function. This is approximation of analog function. When I say continuous, I mean that we can exploit data, information between any time interval. For example, the analog signal can then take any values within a range between a minimum and maximum values. This characteristics is important because this signal can represent exact waveform. As an example, the black marker in this figure, V, allows any precision in y-axis, say 74.8, 74.81, 74.815234, or 74.815233 and other digits later. And the other important thing is that since an analog signal at each point can take values of various precision, it is sensitive to noise. Let's give you some daily life examples. For example, an analog clock gives time by the changing positions of its 3 hands. It means that by rotation of arms, we can have access to infinite values representing time. But digital clocks just gives time in hour, minute, or sometimes in hour, minute, and second. But they do not provide infinite values of time. For example, between these two times, there is no other time between 23rd and 24th seconds. If we use TVs with antenna, as shown here, it means that they receive radio waves of varying amplitude, frequency, and phase in analog form. The received information then represents the brightness, color, and sound that we see on TV. Digital TV is like, say, Netflix. And this is the same as analog and digital phones. I should point it out that communications between integrated circuits or ICs are mostly digital, and signals like HDMI for video are digitalized. Let's dive right into the sampling and quantization procedures. Analog-to-Digital Converter, or ADC, contains mostly 3 steps, as shown here. Analog signal as input is sampled in time. It means that time becomes discrete while amplitude remains continuous. This sampled signal is quantized, at which the amplitude will become now discretized. The last part is about converting the quantized output to a sequence of binary strings. We aim to discretize an analog signal which is continuous both in time and amplitude. This process is called sampling. First, we define sampling period or interval, TS, which is the time that we uniformly measure from the analog signal. This is mathematically a multiplication operation in which the original signal xt is multiplied pointwise to function ct, which is 1 at each ts time, ts seconds, and then 0 in between, as shown in this figure. By multiplying pointwise xt and ct, we get the sample waveform, as shown here. Each vertical line is called impulse. Note that each impulse, or height of each impulse, equals to the instantaneous value of xt at the same time. The resulting signal is then discrete signal with values measured at discrete and uniform time intervals. While here we need to know about sampling theory, I postponed this, as I mentioned, to another video to avoid any complexity for now. Quantization is about discretizing the amplitude into a number of levels in the vertical axis. For this, we need to define, like sampling interval, the quantization levels for vertical axis. Here we define the resolution in vertical axis in terms of bit, say 3-bit, 4-bit, 8-bit. We call then our ADC has, for example, 3-bit code. What does this mean? Let's remind you the meaning of a bit. Everything in a computer is binary, either 0 or 1. A bit is the smallest unit that stores just a 0 or 1. With 2 bits, at each bit we have 2 selections, 0 or 1. For this one, 2, for this one, 2, and therefore the total number of selections or number of levels in vertical axis become 4. N equal 4, the number of levels. With 3 bits, we can store 8 different values. 2 multiply 2 times 2 become 8. Because for each bit we have 2 choices. And then for 3 bits, the number of choices or values or number of levels for quantizing the signal in vertical axis is 8. Now we discretize the vertical axis into 8 levels as shown in this figure. These levels are equidistant and their length, or the length of each level, is the maximum value of signal minus minimum value divided by the number of levels. For this example, which we have the signal between -1 and 1, then the level length become 0.25. We see here starting from -1, minus 0.75, minus 0.5, and so on. We move towards 0.75. We see we have 8 different values and corresponding to 8 different levels, as shown by the gray lines here, horizontal lines. For 3-bit ADC, we have 8 levels, as shown in previous slide. 8 levels are labeled by decimal integer values of 0, 1, 2, 3, 4, 5, 6, 7, as shown here. It means we map from amplitude to a finite number of integer, in this case 8 values from 0 to 7. This is our first mapping, as shown here. Our ultimate goal is getting to digital signal just with 0 and 1. We applied the second mapping by converting the decimal integers to corresponding binary values for our 3-bit ADC. Just to remind you, this table contains the transformation between decimal values and binary codes. And you can see an example of a calculation of the binary code here. This figure shows then the mapping between these 2 representations, as shown here, by replacing the levels from decimal integers onto the binary codes. We see here different binary codes are just replaced by the level number. We are now in the last step for quantizing our signal. The last step is about rounding each instantaneous value, because now we are continuous in vertical axis. Rounding each instantaneous value of the sample signal is done to its closest level. For example, this is one of the sampled value. This is another sample value, another sample value. Let's start with the first sample here that resides exactly on level 4. I'm counting here from 0. Therefore, its quantized value within corresponding sampling interval, which is this interval, will be 4 in decimal unit or 100 in binary code. Next point resides in level number 5, and its value will be 101. Let's move on this point here. It's between two levels, 6 and 7, and we round it to its closest level, which is level 7. We repeat the same procedure for all points and finally get this figure. Last step is encoding step. We convert the digitalized signal in time and amplitude into a sequence of binary numbers as shown for few steps in here, from left to right of this figure, just from here to here. You see this string. Here you can find Matlab sample code in order to reproduce all figures in this video.